Welcome to Deep Dive into Knowledge.
Welcome to Deep Dive into Knowledge. I would like you to pause for just a moment and just observe the room you are in right now. Look at the light falling from a bulb above you or, the screen of the device you're holding. Think about the invisible signals that are traveling through the air at this very second, carrying this audio directly to your ears. We live our entire lives completely dependent on a silent, invisible force that we cannot truly see and that we cannot touch without extreme danger. It is a slightly unsettling paradox when you really sit and think about it. The ordinary power that makes our modern comfort possible, the energy cooling our food and warming our homes, is the exact same terrifying force that our ancient ancestors believed was the direct wrath of the heavens. We walk around completely unaware that our own thoughts, our beating hearts, and the silent wires inside our walls are all animated by that exact same ghostly energy. But something so ordinary actually hides a 2,500-year history of obsessive curiosity, blind luck, and fatal risks. So, how did this actually happen? How did humanity go from staring blindly at a piece of ancient tree resin to actually capturing the power of a thunderstorm?
Well, that journey begins on a really quiet coastline in ancient Greece. We're talking around the year 600 BCE.
Right.
And we have to look at a philosopher named Thales of Miletus. He made an observation about a very beautiful material, which was amber.
Amber, so that's the fossilized tree resin, right?
Exactly. It's this golden translucent resin from ancient trees. The Greeks valued it highly for making jewelry.
Okay.
But Thales noticed something really strange when he handled it. If he rubbed a piece of this amber against some wool or maybe animal fur, the amber seemed to sort of wake up.
Wake up?
Yeah, it came alive. It suddenly gained the ability to attract very lightweight objects. So if you brought the rubbed amber near a feather or dry leaves, they would just jump up and stick to it.
That's fascinating. But my immediate question is, why does rubbing it do anything at all?
Right.
Because, I could rub a piece of wood against my jumper all day long and it won't pick up a feather. What is actually happening there?
That is exactly the right question to ask. Because Thales had absolutely no way of knowing what was happening on a microscopic level.
No, of course not.
It would take another 2,500 years to discover the particle responsible. But we now know exactly what he was doing. When he rubbed the amber, the physical friction forcefully stripped invisible particles, the electrons from the wool.
Oh, okay, so they physically moved.
Yes. They transferred onto the surface of the amber. Different materials hold onto their electrons differently. Wool gives them up easily, and amber grabs them tightly.
So the amber suddenly has too many electrons.
Exactly. It builds up a net negative charge.
Right, I follow that. But how does simply being negative allow it to reach across empty space and pull a feather? The feather hasn't been rubbed.
Well, it happens through a beautifully simple process called polarization.
Okay.
When that negative amber comes near the neutral feather, the negative charge pushes away the negative electrons inside the feather, like charges repel.
Right.
So the electrons in the feather retreat to the far side. This leaves the side of the feather closest to the amber with a slight positive charge.
Oh, wow. So it creates an opposite charge locally.
Spot on. And because opposite charges attract, that positive side of the feather is strongly pulled toward the negative amber. It just leaps through the air.
That is brilliant. It's basically bullying the particles inside the feather to move.
That is a great way to put it, yeah.
And what's truly fascinating to me here is the language we use today. Because the ancient Greek word for amber was actually electron.
Yes, it was.
From that single Greek word, spoken on a beach thousands of years ago, we get the modern word electricity. Every time you say electricity, you were literally just saying the ancient word for amber.
The perfect linguistic fossil, isn't it? But what makes this era even more interesting is that the Greeks also noticed something else at the same time.
Oh, what was that?
They observed naturally occurring dark stones from a region called Magnesia. We call this magnetite today.
Okay, the lodestones.
Exactly. These stones possess their own mysterious power. They could naturally attract heavy pieces of iron.
But without the rubbing.
Right, no rubbing required. They just permanently pulled iron towards them.
So they're sitting there with two completely separate mysteries. They have rubbed amber pulling feathers and lodestones pulling iron.
Yeah, both involving an invisible force acting at a distance. But they didn't connect them at all.
No, of course not.
They saw them as completely unrelated. And sadly, it took more than 2 millennia to understand they were connected. For centuries, the amber effect was just a minor intellectual puzzle.
It's just a huge, almost frustrating gap in human progress, isn't it?
It really is.
It's a 1,700-year gap where humanity just observed this party trick and forgot to investigate it until around the year 1600, right? With William Gilbert.
Yes, William Gilbert. He is a truly crucial figure. He was a very prominent English physician.
He worked for royalty, didn't he?
He did. He served as the personal physician to Queen Elizabeth I. But in his private time, he obsessively conducted experiments with lodestones and amber.
And he finally started to systemize it.
Exactly. In 1600, he published a massive scientific work called De Magnete, meaning on the magnet. He was the first person to draw a clear distinction between magnetism and electricity.
So he proved they were different forces.
He did. He pointed out that magnets only worked on iron, and it was a permanent property. You didn't have to activate a magnet.
Right.
But electrical attraction, he found, could be produced in lots of materials: glass, sulfur, wax. But they all strictly required that physical rubbing.
So it wasn't just magic tree resin, it was universal. But how did he even measure something as weak as rubbed wax?
He had to invent an instrument for it. He called it a versorium.
A versorium.
Yeah, it was basically the world's first electroscope. It was a very simple, lightweight metal needle balanced on a point so it could rotate freely like a compass. If you brought an electrified object near it, the needle would swing to point at it. It let him detect really weak electrical attraction.
That's incredibly clever.
It was. And he needed a word to describe this specific force. So he coined the Latin term electricus.
Which literally translates to, like, amber.
Precisely. Later, scientists adapted his Latin term into the English word we use today.
He gave us the foundation.
Yeah.
But it still feels very quiet at this point. It's confined to laboratories and wealthy philosophers.
It was, yeah.
But by the 18th century, the tone changes completely. We move from quiet study to loud public entertainment. It goes from science to spectacle.
Oh, absolutely. The 18th century is when electricity captured the public's imagination.
Let's talk about the traveling shows. And this thing called the Leyden jar. What was actually happening then?
Well, you had these traveling showmen calling themselves electricians. They toured across Europe and America.
Just entertaining crowds.
Yeah. They weren't rigorous scientists. They built these large machines with rotating glass globes that rubbed against leather pads to generate massive amounts of static electricity.
And what would they do with it?
They'd perform incredible feats. They would make visible sparks fly from a person's fingertips. Or they'd have a dozen people hold hands, pass a current through them, and make everyone jump at the exact same moment.
Wow, that sounds terrifying and fun all at once.
This is pure theater. But the most important device they used was the Leyden jar, invented around 1745.
The first capacitor.
Exactly. The world's first capacitor.
Okay, let's unpack that for a second. Because when I hear jar and storing electricity, my brain pictures someone pouring lightning into a glass like water.
Right, which isn't how it works.
Exactly. Electricity isn't a liquid. So what is actually happening inside that glass? How does an 18th century jar hold a shock?
It is remarkably simple. It's just a normal glass jar, but it's coated on the inside and the outside with thin metal foil.
Inside and outside. Okay.
All right, and the glass wall acts as an insulator. It's a barrier. A metal chain hangs down into the jar, touching the inner foil.
So you feed the static electricity into that chain?
Yes. The inner foil fills up with negative electrons, but because of the glass, they can't cross over to the outer foil. They are trapped.
Just building up pressure?
Immense pressure.
Yeah.
And just like Thales amber, that massive negative charge inside pushes the electrons away from the outside foil.
Leaving the outside highly positive.
Spot on. So you have a massive tension. Huge negative inside, huge positive outside, separated by just a few millimeters of glass.
It's like pulling back a really heavy bowstring and just holding it there.
That is exactly what it is. And when someone touches the outer foil with one hand and the central chain with the other, their body becomes the bridge.
Oh, no.
Yeah. All that frustrated electricity instantly rushes through their body to reunite. It produces a violent shock.
That sounds genuinely dangerous.
It was. One of its inventors, Peter van Musschenbroek, accidentally took a full shock. He was so shaken, he told a colleague he wouldn't take it again for the entire Kingdom of France.
I don't blame him, but the public loved the thrill of it.
They couldn't get enough of it.
And it was exactly this kind of theatrical show that caught the attention of Benjamin Franklin.
Yes, it was.
Now, everyone has this highly romanticized image of Benjamin Franklin flying a kite in a thunderstorm. But looking at the facts, the line between his scientific genius and sheer recklessness seems incredibly thin.
It was almost non-existent. When Franklin saw these shows in Philadelphia around 1746, he was already a famous, wealthy man.
Right.
But he became obsessed. He started building his own Leyden jars. And he noticed something about the sparks in his lab.
What did he notice?
He looked at the bluish light, the way they branched out, the sharp crackling sound, and he saw they were strongly attracted to pointed metal. Then he looked at a severe thunderstorm. He saw the branching light, heard the thunder, and saw that lightning also struck pointed objects, like church spires.
So he made the connection.
He did. He proposed that the terrifying lightning in the sky was exactly the same electrical fluid he was storing in his little glass jars.
Which European scientists found very hard to believe.
They thought it was absurd.
And the kite was his highly dangerous way to prove it. But we need to clear up a common misunderstanding here. Because in the children's books, lightning directly strikes his kite.
Right.
If a direct lightning bolt had actually hit his kite, that would have been the end of the story, wouldn't it?
Absolutely. He and his son would have been killed instantly. There was no surviving a direct strike through a wire you were holding.
It's just too much power.
Way too much. And we know this for an absolute fact because a year later, in 1753, a Russian scientist named Georg Richman tried to replicate Franklin's experiment indoors.
Oh, wow. What happened?
He set up an ungrounded iron rod reaching to his roof. A glowing sphere of ball lightning emerged from the apparatus, struck him in the head, and killed him immediately.
That is awful. So Franklin was extraordinarily lucky.
Incredibly lucky. What actually happened on that stormy day was much more controlled. He flew the kite near the dark clouds, not into a strike.
Right.
The electrical tension in the air charged the kite.
Mm.
Franklin noticed the loose silk fibers of the wet kite string suddenly standing straight out.
Like hair standing up from static?
Exactly. The rainwater made the string conductive. The charge traveled down to a heavy iron key near the bottom.
And then he touched it.
He cautiously brought his knuckle close to the key, and a visible spark jumped to his skin. He felt the shock and smelled the ozone.
He successfully stored it in his Leyden jar.
He did. He proved the terrifying fluid in the sky and the fluid on the table were the exact same thing.
It's a monumental leap.
It was.
Mm.
And he was also the first to propose that electricity was just a single fluid. Before him, they thought glass had one fluid and resin had another.
Oh.
Yeah. Franklin said no, it's one fluid in everything. An excess of it makes an object positive, a deficiency makes it negative. We still use his exact words today.
That's brilliant. And he immediately used this to save lives, didn't he?
He did. He invented the lightning rod.
The first truly practical application.
Exactly. A pointed iron rod on a roof connected by a thick wire into the moist earth. It safely guides catastrophic strikes into the ground. It saved countless buildings from burning down.
It's a wonderful progression. We found it in a stone, captured it from the sky, and stored it in a jar. But all of this electricity is always explosive.
Yes, it's static.
It's a violent spark, and then it's gone.
Yeah.
To build our modern world, they had to find a way to tame it, to make it flow calmly.
Absolutely.
And this leads us to one of the most unexpected twists in the story. It involves a dead frog, the metallic taste of electricity, and the search for the literal spark of life.
It is a bizarre chapter.
Let's move to the 1780s, to Luigi Galvani. What was happening in his laboratory in Bologna?
Well, Galvani was a highly respected anatomy professor. He was studying the nervous system of animals, trying to understand how thoughts translate into muscle movement.
Okay.
He was working daily with dissected frog legs. One day, his scalpel, which was made of a specific metal, accidentally touched the exposed sciatic nerve of dead frog's leg.
Right.
And the leg happened to be resting on a plate made of a completely different metal. The exact moment the two metals and the wet nerve connected, the dead frog leg twitched violently.
Big kick.
It kicked upwards as if it had come back to life. Galvani was stunned. He spent years trying to understand it.
I mean, I try to put myself in his shoes. You are studying anatomy and dead tissue suddenly kicks. It must have seemed like magic.
It was profoundly unsettling for him.
How did he interpret it?
He came to a bold but incorrect conclusion. He claimed he had discovered a new biological force called animal electricity.
Animal electricity.
Yeah, he believed living tissue contained its own innate electrical fluid, the literal spark of life generated in the brain.
And that idea really captured the public imagination, didn't it?
In a terrifying way, yes. It's a direct historical fact that Galvani's experiments inspired a young writer named Mary Shelley.
Right, Frankenstein.
Exactly. When she published Frankenstein in 1817, the premise of reanimating dead tissue with electrical currents was a direct reaction to Galvani's lab work.
It's incredible how science and culture weave together like that. So Galvani fully believed the frog itself was generating the electricity,
He did.
but Alessandro Volta looked at the exact same frog and strongly disagreed.
Yes, Volta was a brilliant physicist, and he was highly skeptical. He suspected the frog was doing nothing special at all.
What did he see that Galvani missed?
Volta noticed in the notes that the violent twitching only ever happened when two different types of metals were used together.
Ah.
He deduced the electricity wasn't biological, it was purely chemical. It was coming from the metals.
So the frog was just acting as a bridge.
Exactly. The dead frog leg was just a wet conductor of salty moisture that let a chemical reaction occur between the metals.
Wow. And he went to extreme lengths to prove this, didn't he?
He did. He wanted to remove the frog entirely. So he took coins made of two different metals, a silver coin and copper coin,
Right.
and he placed them directly onto his own tongue.
Just straight on his tongue.
Straight on his tongue, making sure the metals touched. He used his own salty saliva as the wet conductor.
That is so strange to modern ears. What happened?
When he did this, he experienced a distinct, sour, metallic taste.
Which was the electricity.
Exactly. That sour taste was the physical sensation of a mild electrical current flowing across his tongue. He proved you didn't need animal nerves. You just needed two different metals and a conductive liquid.
That sour taste leads directly to an invention that changes everything. Because if the shift from sparks to a steady flow is like moving from catching lightning in a bottle to turning on a tap of water, how did Volta actually build that tap?
In 1799, he took that principle and built the voltaic pile, the world's very first true battery.
How'd he build it?
It was elegantly simple. He took a small disc of copper, placed a disc of zinc on top of it, then a disc of cardboard heavily soaked in salt water on top of that.
Okay, so metal, wet cardboard.
Exactly. And he just repeated it. Copper, zinc, wet cardboard. He stacked them up into a tall tower, a pile.
And that generated power.
When he connected a wire to the top and bottom, a steady, continuous, measurable flow of current traveled through the wire.
Not a quick spark.
No, a reliable, unbroken river of power. As long as the chemical reaction continued, the electricity just kept flowing.
The impact of that must have been immediate. You suddenly have a tool you can live running on a desk.
It completely revolutionized science overnight.
Yeah.
By 1800, chemists realized that if they ran this steady current through water, the pressure would physically tear the water molecules apart.
It split the water.
It literally split it into hydrogen and oxygen gas. It proved for the first time that water was a compound, not a fundamental element.
That's amazing.
Another chemist, Humphrey Davy, used massive, room-sized voltaic piles to tear dense minerals apart, discovering entirely new chemical elements like sodium and potassium.
So the battery was like a scalpel made of pure energy.
Exactly. And Napoleon was so amazed he made Volta a count. To this day, we measure electrical pressure in volts in his honor.
So we finally have this continuous river. But if you think about a real river, you need to understand how the water behaves under pressure to use it safely. You need mathematics.
You absolutely do.
You can't just connect a massive battery to a tiny wire without something melting. This brings us to Georg Ohm in 1827. What did he figure out?
Georg Ohm provided the mathematical blueprint for every circuit ever built. He published Ohm's law in 1827.
What are the rules?
He realized a circuit involves three fundamental properties locked together: voltage, current, and resistance.
Okay, let me try a water pipe analogy because that helps me.
Sure.
The voltage is like a water pump pushing water into a pipe. The current is the actual water flowing, and the resistance is the width of the pipe.
Right.
So if I have a really narrow pipe, high resistance, I need a much stronger pump or higher voltage to force the same water through it. Is that accurate?
That is a perfectly accurate analogy. Ohm's law states that current is exactly equal to voltage divided by resistance.
It sounds simple now.
It does. But then it was a profound revelation. It meant electricity obeyed strict mathematical rules. Engineers could calculate exactly what they needed without burning the wires.
It made precise engineering possible. But there is still a massive problem here.
The batteries.
Exactly. The power is coming from chemical reactions. Batteries run out, they die. If humanity was stuck relying on batteries, the modern world of brightly lit cities couldn't exist. We needed to generate power endlessly.
Yes, we needed a generator.
And this is where we meet Michael Faraday, a man with an intuitive genius that borders on the miraculous. How did a poor bookbinder's apprentice figure out what trained scientists could not?
Faraday's life story is one of the most inspiring in all of science. Born in London in 1791 to a poor blacksmith's family, he had almost no formal education.
None at all.
Very little. At 13, he became a bookbinder's apprentice. He just sewed pages together all day.
But he read the books.
He read everything he bound. Encyclopedias, early chemistry. In 1812, someone gave him tickets to science lectures at the Royal Institution, given by Humphrey Davy.
The same Davy with the giant battery.
The very same. Faraday sat there, completely captivated, taking meticulous notes. He bound his notes into a beautiful leather book and sent them to Davy.
Basically a silent job application.
Exactly. And Davy was so impressed, he hired Faraday as a lab assistant. Faraday started sweeping floors, but eventually became far more consequential than Davy himself.
That is an incredible journey. And he had a specific puzzle he wanted to solve regarding magnets, right?
Yes. Scientists knew electricity could create a weak magnetic field. But Faraday wanted to know if it worked in reverse. Could a magnet create electricity?
Which is the great unsolved question.
Right. People tried placing strong magnets next to wires, but nothing happened. A stationary magnet does nothing.
So what did Faraday do differently in 1831?
He took a solid iron ring. He wrapped a wire coil on one side connected to a battery. On the other side, a separate coil connected to a dial that detects current. The wires never touched.
Okay, so just iron between them.
When he turned the battery on, the dial on the second coil flickered briefly, then dropped to 0, even though the battery was still on.
That's strange.
When he turned the battery off, the needle flickered again in the opposite direction.
Ah.
Faraday realized it wasn't the mere presence of a magnetic field, it was the change in the field. The expanding and collapsing of the field pushed the electrons.
So motion was the key.
Motion was the absolute key. A static field does nothing. A moving field does the work.
And he simplified this into a desktop experiment, didn't he?
He did. He took a hollow coil of copper wire, connected it to a meter, and physically thrust a plain bar magnet into the coil.
And the current flowed.
The meter jumped immediately. He held it still, the meter dropped to 0. He pulled it out, the meter jumped the other way.
It is stunning. The mechanical energy of his hand was converted directly into electrical energy.
Exactly. He had discovered electromagnetic induction.
And he did all of this purely by observing. He couldn't rely on complex math.
That is the most staggering fact about him. Because of his background, he had virtually no mathematical training beyond basic arithmetic.
He couldn't write the calculus equation.
He couldn't. So instead, he used his vivid imagination. He visualized invisible lines of force extending out from the magnet, like rubber band.
And when the wire cuts across the bands?
The cutting action forcefully pushes the electrons. Educated scientists dismissed this as unscientific, but his physical intuition was completely, flawlessly correct.
He gave us the ultimate mechanism. If you keep a magnet moving near a wire, you have infinite electricity. No batteries needed.
Exactly.
But proving that on a desk is very different from powering a civilization. You have to spin those massive magnets with immense force and deliver the power safely to millions of homes.
Which brings us to the late 19th century.
Yes, the war of currents. We move from the polite laboratory to the ruthless boardroom. On one side, Thomas Edison. On the other, Nikola Tesla and George Westinghouse. How did this battle begin?
It began with Edison's grand vision. In 1879, he developed a practical light bulb. But he knew bulbs were useless without a power grid.
Right, you need the infrastructure.
He had to build the stations, lay the cables, invent the meters.
Mm-hmm.
In September 1882, he opened the Pearl Street Station in Lower Manhattan.
The first commercial power plant.
Yes. They burned coal to boil water. The steam spun heavy engines, which spun massive magnets inside giant coils of wire, doing exactly what Faraday did by hand.
Just on an industrial scale.
Exactly. He started lighting up Wall Street businesses, and it seemed like a total triumph.
But there was a crippling flaw in Edison's design, based purely on the physics of direct current.
Yes. Edison committed entirely to direct current, or DC. The electricity flows continuously in one constant direction. It's reliable, but it has a fatal limitation for a city grid.
What happens over long distances?
As DC travels through long copper wires, the natural resistance causes the electrical pressure, the voltage, to drop significantly. It gets lost as waste heat.
So it just fades away.
It does. Edison's Pearl Street Station could only push electricity about 1 single mile before the voltage dropped too low to light a bulb.
1 mile.
Just 1 mile. If you wanted to power London or New York with DC, you would literally have to build a loud, polluting, coal-burning station every single mile right inside residential neighborhoods.
That is wildly inefficient.
Incredibly expensive and inefficient.
Which is where the alternative completely upends his monopoly. Alternating current, supported by Tesla and Westinghouse. How did their system solve this geographical problem?
Tesla was a brilliant engineer who actually worked for Edison briefly before leaving. He partnered with Westinghouse to champion alternating current, or AC.
How does AC flow differently?
The flow doesn't go smoothly in one direction. It rapidly and violently reverses direction, washing back and forth through the wire maybe 50 or 60 times a second.
Okay, and why is that better for long distances?
Because AC can easily pass through a device called a transformer. A transformer can magically alter the voltage. It takes the power from a plant and steps it up to incredibly high, dangerous voltages.
Which overcomes the resistance in the wires.
Exactly. It can travel hundreds of miles along elevated lines with very little energy lost. Then, when it reaches a city, another transformer safely steps it down to a low voltage for homes.
So you don't need a dirty power station every mile.
You can build one massive station far away, like next to a waterfall, and transmit the power efficiently. The physics of AC were undeniably superior.
So Edison is faced with a competitor who just has better physics. And it is a dark, tragic irony that Edison resorts to absolute fear-mongering to protect his patents.
He really did.
If you look at the gray cylinder on the telephone pole outside your window, that is literally a monument to the end of this war. It's a transformer stepping down the AC power. But what lengths did Edison go to in order to protect his empire before he lost?
Instead of adapting, Edison launched a PR campaign of shocking ferocity. Because AC used high voltages, he loudly claimed it was a deadly menace. He wanted people to believe AC lines would kill them in their beds.
Which is just dishonest.
It was. And to forcefully prove his point, Edison and his supporters began organizing gruesome public demonstrations.
What did they do?
They would intentionally electrocute animals, stray dogs, calves, even a horse, using alternating current in front of reporters.
That is deeply grim.
He wanted the press to report on the lethality of his rival system. He even secretly lobbied New York State to have the first electric chair run exclusively on alternating current.
Hoping to link the Westinghouse name to death.
He literally wanted people to call death by electrocution being Westinghoused.
It is a truly dark chapter, but ultimately, physics cares nothing for public relations. The better system has to win. Where was the decisive victory for AC finally won?
The turning point was 1893, at the World's Columbian Exposition in Chicago.
The massive World's Fair.
Right. They wanted to illuminate the entire fairground. Westinghouse won the contract because his AC system was vastly cheaper to install.
It worked.
Flawlessly. Visitors walked through a landscape blazing with over 200,000 bulbs. It proved to the world that AC was safe and scalable.
And that led to Niagara Falls, right?
Yes. Just 3 years later, in 1896, Westinghouse and Tesla built a massive hydroelectric plant at Niagara Falls.
Wow.
They successfully transmitted the alternating current to power the city of Buffalo, which was 42 kilometers away. Edison's DC could never have crossed that distance.
The war was over.
It ended right there. And to this day, our global grid runs on the exact principles Tesla and Westinghouse championed.
We've seen it evolve so much, from rubbing amber to a continent-spanning grid, but we're still looking at electricity and magnetism as two separate phenomena. We need someone to unify them.
I mean, James Clerk Maxwell.
Exactly, the mathematician. In 1865, how did he pull all these pieces together?
While the commercial war was brewing, Maxwell, a quiet Scottish physicist, was reshaping our understanding of the universe. He was an absolute master of advanced mathematics.
And he looked at Faraday's work.
He looked closely at Faraday's intuitive lines of force. Maxwell realized Faraday's physical intuition was right, but it needed formal mathematical proof.
So he wrote the equations.
In 1865, he published 4 elegant equations, Maxwell's equations. They perfectly describe the unified behavior of electric and magnetic fields.
So they aren't separate forces at all?
No, they are two sides of the exact same coin. A changing electric field creates a magnetic field, and vice versa. They are inherently intertwined into one single force, electromagnetism.
And when he ran the numbers on these fields, waving back and forth, he made a discovery about their speed that completely altered our understanding of reality, didn't he?
It's one of the most beautiful moments in science. He calculated the exact speed at which this invisible electromagnetic wave would travel through space.
And what was the number?
Approximately 300,000 kilometers per second.
Which is the speed of light.
Exactly. He recognized the number immediately. Light had been measured before, but no one knew what it was made of. Maxwell proved definitively that light itself is simply an electromagnetic wave.
That is breathtaking.
It means, and the visible light by which we see the world are all manifestations of one single unified phenomenon.
So when we turn on a light bulb, the electricity in the wire is made of the exact same fundamental stuff as the light shining out of the glass.
Exactly the same.
It's incredible. And speaking of generating electricity today, despite computers and space travel, we are still largely relying on Faraday's 1831 discovery. We split the atom just to boil water, to make steam, to spin a magnet in a coil of wire. It's all still Faraday's wheel turning.
It is entirely true. If you look at a modern massive thermal plant, coal, gas, or nuclear, the underlying physics hasn't changed since Faraday thrust that magnet into his coil.
The fuel is just different.
Right. In a nuclear plant, we split atoms to generate immense heat. But that heat just boils water. The steam rotates a massive electromagnet inside copper wire coils, generating alternating current. Faraday could walk into a nuclear plant today and understand the generator instantly.
But there are newer ways that bypass the spinning magnet entirely, like solar power, that relies on a different mechanism, doesn't it?
Yes, solar power breaks the reliance on heavy mechanical machinery. It uses a quantum mechanism called the photovoltaic effect.
When was that discovered?
Surprisingly early, 1839, by a French physicist named Edmond Becquerel. He found certain materials generate a small electrical current when exposed directly to bright light.
How does the light make a current?
The energy of the incoming light physically knocks electrons loose from their atoms, creating a steady flow.
But it took a long time to become practical.
Over a century. It wasn't until 1954 that researchers at Bell Labs created the first practical silicon solar cell. Today, it's the fastest growing source on the planet. The sunlight silently strikes the panel and directly pushes the electrons.
And looking forward, we are trying to take the final step. Replicating the sun itself here on Earth, nuclear fusion. This seems to be the ultimate frontier of power.
It is the great hope for the future. Current nuclear plants use fission splitting heavy atoms like uranium, which leaves dangerous radioactive waste.
Right.
Fusion does the exact opposite. It takes very light atoms, hydrogen isotopes from seawater, and crushes them together under immense heat and pressure until they fuse into helium.
Which is what powers the sun.
Exactly. It releases staggering amounts of pure energy with zero greenhouse gases and very little waste.
But it's difficult to achieve.
The challenge has always been that it takes massive electrical energy just to create the heat needed to start the reaction. But recently, researchers achieved a historic milestone. They recorded a net energy gain.
They got more energy out than they put in.
For the very first time. If we can engineer this into practical power plants, we will have a nearly inexhaustible supply of clean electricity drawn from the oceans, mimicking the stars themselves. When we look back across this entire expanse of human history, from the ancient coastline to the fusion reactors of tomorrow, a very clear pattern emerges. Electricity was never invented.
No, it wasn't.
No single person created it from nothing. It was discovered, revealed to us slowly through thousands of years of deep curiosity and immense risk.
From Thales to Maxwell.
Exactly. Thales observed it in amber. Gilbert gave it a name. Franklin proved the flashes in the sky were the same phenomenon. Volta forced it to flow. Faraday learned to summon it with a magnet. Ohm wrote the mathematical laws. Edison and Tesla built the immense system, and Maxwell proved it is woven into the very fabric of light itself.
It was always there.
In the fossilized resin, in the clouds, in the electric eel, and firing quietly in every single nerve cell of your own body right now. The true triumph was finally understanding it well enough to strip away the ancient fear and turn it into the most fundamental tool civilization has ever possessed.
The soft light that is letting you see your surroundings right now. The device resting calmly in your hand. The massive grid that connects our voices across the world. And the very firing of your brain cells as you process the meaning of these words. All of it traces back in one unbroken, beautiful line of inheritance. It all leads back to a Greek philosopher standing on a quiet beach, rubbing a piece of tree resin against a cloth, and noticing that a simple feather moved. It is a quiet but important truth. We're walking around every day, completely swimming in an ocean of forces that we barely comprehend. So here is the question to leave you with today. If a force as immense, as world-altering, and as vital as electricity was always sitting right there, hidden silently inside a small piece of amber and buried in the storm clouds above our heads, what other forces of comparable power might be surrounding us right now, just waiting for someone to notice the right pattern, ask the right question, and be willing to fly a kite in a storm?